For our senior project, we decided to design and build a remote control Baja car for the Student Professional Development Conference. Each one of us designed, tested, and built each of our own components.
My name is Seth Whitson, and I did the frames of the RC Baja car. The engineering problem I faced was that RC Baja cars seem to break during head-on collisions quite easily. So it was my idea in solving that problem to make a frame that absorbs energy during head-on collision. My design requirements were to use 3 springs to dissipate energy, have 1.5 inches of internal travel, for the frame to weigh no more than 2 pounds, abide by all the competition rules, and accommodate all other car components. My initial goal was for the car to bottom out, or for the suspension in the frame to bottom out at a head-on collision at 15 miles per hour. That was with a 5-pound car and a K-factor in one spring of 134 pounds force per inch. I also wanted the frame to look like a regular frame. I decided to put the springs inside the frame, as you can see it going up and down, like in the video here. When I was building it, I wanted it to have high manufacturability, which means I didn't want it to have any complex curves, and I wanted everything done manually. When I was building the frame, it turned out to be 9 parts in one assembly. All the parts, except for the springs, were constructed at CWU. And as you can see, here's the 9 parts, and the springs are missing out of this. But they all go together, as you can see on that exploded view in the SolidWorks drawing. The part manufacturing took less time than I allotted, but the assembly took more time. During the competition, the car and the frame performed very well. The only flaw that it had is that one pin sheared during the competition when it hit. But that's a minor flaw, and the pins can be re-engineered so they won't break. I had 2 tests for the car, for the frame. One test was weight versus frame travel, and this shows that the frame will bottom out with 55 pounds mass. So converting this to a dynamic problem with a 7-pound, 4.5-ounce car and the new springs being 22.96 pounds per inch, this converts to 7.7 miles per hour. The car will bottom out, or the frame will bottom out. The steering radius testing, which was a perk of this frame, I figured that I could shorten the wheelbase by pinning the frame all the way back and have a tighter steering radius. It turns out this is true. With the frame shortened by 1.5 inches, the car gains 13.3% tighter steering radius. You can see here in my testing table that here are the calculated velocities for the weights of that were put on the frame. It was done with an energy equation and percentages. And down here is the steering radius testing, which shows similar things with the uncompressed frame and the compressed frame's steering diameters, and then converts radiuses, and then the percent difference. My budget and hours were a little off. The frame originally budgeted to $80. Due to the miscellaneous category and the 4 projects not perfectly overlapping, the budget was off by a long shot and ended up being 310% over budget and costing $247.98 just for my frame project. The allotted amount of time was 211 hours done in an Excel spreadsheet, as you can see here with the chart and schedule. And I went over to 284 hours, which was 135% of the original allotted time. little discussion about the frame. According to the success criteria in my final report, the frame was successful. There was at least 1.25 inches of frame travel, and the car sustained only minimal damage after a head-on collision at up to 15 miles per hour. Also, according to the benchmark analysis, the frame was a success because there was damage avoided due to the compressible frame. In conclusion, although all the design requirements weren't met, the frame is still considered successful. The overall performance was great, and the car never sustained any major damage from any collision. Thank you.
For my senior project, I designed the RC Baja suspension system. After doing the SBDC conference last year, I had a couple benchmarks that needed to be addressed. I needed the suspension to weigh less than a pound overall, have an average of 3 inches of wheel travel, and be able to withstand an impact of a 7-pound car going 30 miles an hour, which equates to around 480 pounds of force. Along with those 3 criteria, I also stated that I needed to keep the budget under $400, which was difficult at times. I started off in designing. In my original design, I made things overcomplicated, unmachinable, if you will. So after many nights of sleeplessness, that's a good word, I went back to the drawing board and simplified all of my designs. And I came up with this. These are my upper control arms. For the front and the rear, they had to be different. So even though I was using CNC operations to cut out my parts, I still would have to write the G code for both the front and the rear upper control arms. The lowers themselves were a little bit more complex. They were made of thicker material so that they could support the load that would be applied to them when the car hit something. Another issue that I had to address in my design was where I was going to mount my shocks and how the shock towers were going to sit on the frame and how everything was going to drive together. So I came up with this design for my front suspension mounts. There's 2 of them, and they have pins that go in between them, and then the shock mounts perfectly in between them. This is the completed sub-assembly for the rear of the car. You'll notice that it will look different than this one, which is the completed front assembly for the car. And that's the completed front sub-assembly after machining. One of the major things that we did in designing the car was we used SolidWorks, and we assembled the entire car in SolidWorks so that we could try to troubleshoot some of the issues that we knew that we were all going to have before they became an issue. So this is our frame, what would be a rolling chassis if it were tangible in real life, but it's not. Another thing that was done for my project, I tried to optimize my suspension by finding out what was a good length to have, what was a good width to have, so that the suspension could support as much weight as necessary without failing. And so that's what I did. And then I ran a finite element analysis through SolidWorks to just get a ballpark for a deflection with my basic design that I had thus far. After the design was complete and finalized, we went on to the manufacturing side of things. And show you some of my pictures. Everything for the suspension was done using the CNC Miltronics downstairs. This is the rear suspension mount in the back. That was CNC. This is the machining of the lower control arms. The finished control arms, just wanted to show that they're not water jetted. They are all made from a mill, essentially. And the completed front assembly. This is a short little video here of the machining process. Sorry for the quality. So one of the major things for my suspension system was the testing. Along with the competition, I wanted to do some testing of my own. The testing consisted of hanging weights off of the end of the control arm and measuring the deflection with a dial indicator. So these are just a couple pictures of the setup that I used. the weights I used. I graphed the load versus displacement, which it's just gives you an image of what it linearly, how it's going to linearly displace. And then I calculated the stress versus the strain with the data that I have, and what I found out was that I designed my suspension components properly, in the sense that the stress versus strain graph is linear, which means that the suspension never yielded or went out of the elastic range, which is a very important point that should be brought up. These are pictures from the competition. The suspension system was necessary, and when I designed the suspension system, I wasn't planning on this rigorous of a course that we were going to be going through, but as you can see, obstacles 6 feet in the air, it was really put to the test, and for the amount of time and money that I put into the project, I would deem my suspension system a success based upon the criteria that I only went $86 over budget. My time was 186 hours, and out of the 16 cars of the competition, our car was one of the 4 cars that didn't break. So my project was a success. The suspension system did not fail.